Greetings. The purpose of this short video is to highlight a newly introduced component in the digital signal processing library. In particular, we'll be talking about digital pre-emphasis filter, DPE filter for short. This is a digital filter, or it could also be an analog filter, that performs pre-emphasis. It takes in an electrical signal and has an output electrical signal. The theoretical foundation for this filter is fairly straightforward. In the channel, for example, we have an uncompensated filter shown here in red. This could be a bandwidth limitation on a driver, digital analog converter, or any electrical component in the path of the electrical signal. This particular red response for this uncompensated filter will cause penalty in our simulation model. To compensate for this low-pass filter effect, we would like to include a high-pass filter to take out this low-pass filtering effect. And this is where the desired filter comes in. So as we see here, two examples of desired filters in blue, and typically these desired filter responses should accommodate the bandwidth of your modulated signal. And in this case, for example, we have here that a desired filter for a 32 gigahertz bandwidth, and the uncompensated filter is 16 gigahertz bandwidth. So there is this bandwidth difference that we want to compensate for. The formula for this digital pre-emphasis filter is essentially the desired filter divided by the uncompensated filter. Now, for the denominator term, we're adding this N0 term, which is a noise compression term that allows you to control the amount of high-pass filter for the very high-frequency components as to limit the amplification of noise. So this is an adjustment term that's included inside the component. The digital pre-emphasis filter here is evaluated for a few of the bandwidths for the desired filter. So if the desired filter is high in bandwidth for the uncompensated filter to 16 gigahertz, then you would require a higher and higher digital pre-emphasis peak. And in this simple example, we'll overview some of the parameters inside this component. So for the main tab, we have this noise adjustment term described earlier, and we have the typical parameters involved in any filter, an optisystem, insertion loss, and a depth. We have a tab for the uncompensated filter response, and here we have an option of actually selecting up to 9 different filters for the uncompensated response, allowing you a lot of flexibility in targeting a variety of filters or bandwidth limitations that impair your transmission. And we also have the cutoff frequency for these filters and the order. Some of the additional parameters here become visible under certain conditions. For example, if you are operating with a raised cosine, then you have your symbol rate and the roll-off factor, and maybe some other filters would have the ripple factor enabled as well. And you can also have the uncompensated square root to do a root raised cosine filtering, for example. So this is a fair bit of flexibility here in targeting an uncompensated filter response. The desired filter response also have this very similar flexibility, and you can select up to 9 different varieties of the desired filter. As such, the component can really have up to 81 various combinations of the two filters for either desired and uncompensated that gives you an ability to target a variety of scenarios in your modeling and simulation. For the FIR implementation tab, without FIR being enabled, the uncompensated filter will actually behave as an analog filter. However, if you would like to include some digital signal processing implementation, then you can enable FIR implementation, and the component will take your optimum digital pre-emphasis filter and calculate from it coefficients that could be then used in a digital filter or implemented in your experimental setup. And it actually performs this back calculation from the response that's been targeted with a specific tap resolution and specific number of taps. You also have an option to select the various windowing methods from Hamming to Han and Bachmann to be able to extract those FIR tap coefficients. And you can save these coefficients into a file that can be then used to run digital filter or use for additional simulations and experimental validation. Furthermore, the filter could be enabled or disabled with the typical Enable in the Simulation tab. Now we'll attempt to run the simulation with default settings. And if you click on the main tab here, you can see that we're running a noise adjustment term of 0.12 and insertion loss is 0, depth is 100. The uncompensated filter is a Bessel filter with 16 GHz bandwidth and a third order. The desired filter is a Gaussian filter with a 24 GHz bandwidth and second order. As you can see that the desired filter is a higher bandwidth than the uncompensated filter. And in this first run, we will have the FIR disabled. As such, this will act as an analog filter. And if we run the simulation, you'll see that right away, if you go to the component view and have observations about the 2D graphs, you'll see the uncompensated filter transfer function. So this is the filter that's limiting our performance, and we would like to enhance the signal or pre-compensate this filtering response. This is the desired filter. This is the target filter in green that we want to have the signal within its current modulation bandwidth. In blue here, we see the digital pre-emphasis filter. This is the actual filter implemented in the component. And as you can see here that it has this signature increase and then decrease, so high pass filtering effect. And the purpose of this blue filter is really to compensate the effect of the red filter for the targeting the green filter. This is an analog filter implementation, and as such, one can observe the impulse response of such a filter here. This is your DPE real and imaginary impulse response. You can certainly increase the resolution in the time domain by increasing the number of time samples and have a higher resolution for an analog impulse response. Subsequently, if we'd like to do a digital implementation, we can certainly go into the component and implement it using Enable FIR. And we can see here that the FIR sample rate is taken from the global, scripted from the global sample rate. We'll do 128 FIR taps with 12-bit resolution, and we're using the Bachmann windowing method in this particular example. Now, with this setting, the filter is a digital filter that can now be viewed, and you can see the FIR real and imaginary of these coefficients. These coefficients can be certainly fed into your experimental setup or fed into a digital filter component that's available in OptiSystem in the filters library, and you could mimic the response of this digital pre-emphasis. You can certainly view here on the 2D graphs of the electrical visualizer, and you can see the response of your particular digital filter, and you have here now some additional artifacts due to the windowing, quantization methods, and the number of taps truncation. If we revert back to the analog implementation of the filter, just for the sake of clarity, and we run the simulation, we can observe the electrical filter analyzer, and you can see now that this is a fairly smooth transition into the stop band without any of the artifacts arising from truncation, quantization, and windowing method. Thank you very much for your attention.